Take a look at this satellite view of Earth. Floating in the void, it looks peaceful, isolated, and safe. But that isolation is an illusion. We live next to a raging nuclear furnace. The sun constantly bombards our planet with a relentless stream of highly charged particles. The reason those particles do not reach the surface is because of the magnetosphere. This is an invisible magnetic bubble generated deep within the Earth's core that catches and deflects that deadly solar radiation around us. Without this specific defense system working around the clock, our blue oceans and green land masses would have been stripped away into a rocky, irradiated wasteland billions of years ago. While this magnetic shield works, it isn't a rigid wall. When the sun unleashes a major solar storm, the magnetosphere gets compressed, fluctuating wildly and violently under the pressure. These intense fluctuations create what scientists call space weather, which can blind our communication satellites, overload power grids on the ground, and expose astronauts to lethal radiation. We have known the magnetosphere exists for over 70 years, yet we have never been able to observe the entire system dynamically as it takes a hit. We have built a modern civilization that relies completely on a planet-wide defense mechanism we cannot actually see. Here is a look at a Vega C rocket sitting on a launch pad in French Guiana. On May 19, 2026, it lifted off, carrying a spacecraft called SMILE into orbit to solve this exact observational problem. Building a spacecraft capable of stepping back to look at our own magnetic field required a massive joint endeavor between the European Space Agency and the Chinese Academy of Sciences. To photograph this planetary bubble, SMILE travels on an extreme elliptical orbit, shooting 121,000 kilometers above the North Pole for a wide vantage point. It then dives back down, skimming 5,000 kilometers above the South Pole to beam its data back to Earth. This extreme roller coaster trajectory is the mathematical compromise necessary to get far enough away to view the armor, yet close enough to send pictures home. The primary tool on board this mission is a massive, highly advanced X-ray camera developed by researchers in the UK and Europe. When solar wind crashes into the outer boundary of the magnetosphere, the collision emits X-rays. This camera maps exactly where those physical impacts happen. At the exact same time, a second instrument, an ultraviolet camera, is pointed firmly down at Earth's North Pole. Here you can see the brilliant green of an aurora borealis. While the X-ray camera watches space, the UV camera stares at the North Pole for 45 hours at a time, tracking how these auroras react in the inner atmosphere as the magnetic storm rages above. It is a remarkably clever two-pronged approach. The X-ray camera watches the outer shield take the punch, while the UV camera watches the inner atmosphere bruise. The real breakthrough happens back on Earth when scientists overlay the X-ray data of the outer impact with the UV recordings of the inner auroras. Combining these datasets creates the first real-time, four-dimensional moving picture of Earth actively reacting to a solar storm. We are moving from guessing how our planetary shield holds up under pressure to watching it perform in high definition. As our civilization pushes further into space, we become entirely reliant on fragile orbital technology that can be wiped out by a single massive solar event. Accurately forecasting space weather is no longer an optional scientific pursuit. It is a strict requirement for maintaining global infrastructure. As ESA Director General Josef Aschbacher notes, crossing international borders and pooling global resources was the only way to build the tools necessary to understand these massive cosmic forces. By bringing our invisible armor into the light, the SMILE mission gives us the knowledge required to keep our grids, our satellites, and our future astronauts safe for decades to come.